This illustration is about nonlinear shooting with Newton's method. That is the the method which is required for solving two-point boundary value problems, and that can also be extended to higher order problems. And in this illustration, we will go through the Microsoft Excel sheet calculations only for the uh, the Newton's method inclusion to the nonlinear shooting. Second order boundary value problem in journal form is written as d2 by dx squared equal to f of x by y prime, and we have been provided with the boundary conditions at the range of x values, the x bounds a and b. So we have y of a equal to alpha and y of b equal to beta. As a quick review, a two-point nonlinear boundary value problem. Uh, it is defined with two distinct boundary conditions, and the solution that we have to look for approximate, that is between the domain of x values from a to b. The nonlinear shooting method, it begins with the uh, solution of solving an initial value problem of same order with the guess value of the slope, and we keep on updating the slope values uh, such that the final value, the value at the boundary x equal to b, is satisfied by the solution of an initial value problem of same order. So the problem can be accelerated. Problem of looking for an optimum value of slope can be accelerated by defining a function g of t, which is the difference of the boundary value beta minus y of td, the value of y at the last point for a given slope value t. So in particular, we are interested in solving the problem g of t equal to 0. So an optimum value of y, an optimum value of t, which will satisfy this equation, would be uh, the goal of our Newton's method. The rest of the shooting method is basically the solution of initial value problem. So the Newton's expression for slope modification is here. So we can find a new value of slope tk plus 1 from the old approximation tk as y of b at tk minus beta divided by dy dt at b and tk. So here we have a problem that dy dt, the derivative of y with respect to t at the final value of x is not available. So we define this as the new variable z. So z of x t equal to partial y partial t of x t. So the Newton's expression becomes tk plus 1 tk y tkb minus beta over z of btk. So here we have a new problem to be solved, that the value of z function for a slope value tk and at final value b. So for that we further compute equations. We define z prime. So it becomes partial squared y partial t squared of x t. So which is f of x, y x t and y prime x t. So here we can then define the second derivative y double prime xt partial f by partial y z plus partial f partial y prime, and z prime. So this is a second order differential equation that we have to solve in order to get the solution in terms of z. We will solve this problem with the initial conditions z at equal to 0 and z prime at equal to 1. So this is important, and it is obvious from our general initial conditions y of a equal to a, so its derivative with respect to t would be 0, and y prime of a equal to t, so its derivative with respect to t would be equal to 1. So let's see a solved problem in Microsoft Excel, and the important thing is to see that how Newton's method accelerates the uh, the search of the optimum value of slope, which is tk. So for that, let's move on to see the Excel sheet calculations. So here we have a problem. D2y dx squared equal to 1 over 8 times 32 plus 2x cubed minus y times y prime. So the final term makes the problem non-linear. We have the boundary conditions y1, y of 1 equal to 17 and y of 3 equal to 43 by 7. We will solve an equivalent or similar initial value problem for a guess value of the slope tk, since it's a second order differential equation. So we define it in terms of as a set of two first order ordinary differential equations. So we have the first part. So y prime equal to u and u prime equal to 1 over 8 times 32 plus 2x cubed minus y u, and we will solve this problem with the guess value of the slope. So for example, I take a guess value and let's take a value equal to 1, and with one value you have to solve this problem with RK4 method. We have to have 8k calculations. So this line is very important, how it should be written. So these calculations should be performed very carefully, and once you have computed these values, then it's a matter of repeating that procedure. So again, you can see how this cell has been computed. This B20 is equal to zero point 0.1 times, zero point 0.1 is the step size. So H times f of the expression f of x, y, u, so which is from the first equation. So a u value has been adopted. You can see this calculation, this cell calculation involves this cell which has been outlined. Similarly, you can check for all of the calculations, and the next step is to repeat these calculations for the whole solution domain. So we will find these calculations performed. Now, since we have in our secant, Newton's method calculation, z of btk should be evaluated. So for that case, we have to solve another problem in z. So that problem is over here, z double prime equal to minus 1 over 8 y prime z minus 1 over 8 y z prime. And when this problem is written in terms of two first order ordinary differential equations, it will be written in terms of z prime and v prime. And we will solve this problem with these initial conditions. A value of z at x equal to 1 should be 0, and a value of v and x at x equal to 1 at the first boundary equal to 1. So again we will perform 8k calculations and the calculation of z and v, and then we have to repeat this set of calculations. Okay. Now in Newton's method, we have all of the calculations ready, so we can get an improved value of tk. So let's see. Since we have the exact solution available from our reference book, it's here. Y of x equal to x squared plus 16 over x. So the values have been generated in column AE, and we have the solution value available in column J, which is of y. So let me just hide these cells, these intermediate calculations, and these intermediate calculations. Okay, we have the exact value and the values of computed values. Well, if we plot these values y from column J and from column AE, so we will have a figure as like this. So we have the blue curve as the exact solution, and we have the approximate solution computed at one slope value as the red one. So now time is to update the solution. So we began with value 1. So I write it here 1. And over here T subscript k plus 1, it is basically the Newton-Raphson's expression with values y t k b, the value which is here. Let me highlight this value. So this value is required in the expression which is written at location n 27, and also we require zbtk. This value is the value of z at the last point. So let me highlight this value as well and see the expression. So at n27, we have the n26 value, which is the previous slope value, and the rest of the values, if I make a double click on it, so it will highlight that a value at this point, a new slope value has been generated from old slope value. Please notice the outlined cells. It requires the boundary value 14.333, which is beta value. Then ytkb, this value is adopted from this cell, and a value has been adopted from this cell. So now let's see the approach to the solution. The new value of slope suggested by Newton's method is minus 16.973. So I will provide this value over here, minus 16.9793. So let's see the effect on the solution. So the solution has been shifted to the other side of the curve. However, it is not accurate, so we have to go for the next iteration. So for that case, we began with the slope minus 16.9793. So minus 16.9793, this value suggests a new slope minus 14.2052. So we will again solve the second order initial value problem, which is similar to our boundary value problem, with a new value of the slope again converted into yu prime and all that. So at this stage, let's solve the problem at the new slope value minus 14.2052, and by pressing an enter key you will find the all of the calculations will be modified. That is the power of programming. Of course, in Microsoft Excel, we have to manage some of the things in manual mode. They can also be programmed in the advanced programming languages like uh, anyone that you have been familiar with. So let's see the solution. Okay, it has got closer to the real exact solution. However, let's go for another iteration. So our point will be 14.20552, 14.2052. So it suggests a new slope value minus 14.0028. And with this slope, now we have further improved the solution. We can also see the solution value, the improvement to the error calculations. So now everything is in front of you. Uh, so if I use this slope value minus 14.0028, so it suggests a new slope value minus 14.0002, and now you can see the new value of slope suggested is also the same. No, not here. If I write here minus 14.0002, so yes. So the slope value, the old slope value and the new slope value suggested they are the same. It means no further improvement is available, is possible. And if we look for the errors, so we have approached up to 10 raised to the power minus 5 number, so which is practically um, same as the exact solution. And if you like, you can see the figure. So almost no difference from the previous calculation. So that is the power of that's how we integrate the knowledge of initial value problem solution strategies and the Newton's method or secant method. So it should be noted that the acceleration in Newton's method is higher than the acceleration in the secant method uh, in pursuit of search for the optimum value of TK. It is also important to note that the method that we have learned from nonlinear um, shooting method, they are also applicable to linear problems. However, if you compare the effort, so that is slightly higher. In case of linear problem, the non-linear shooting methods are slightly expensive.